Hey guys, Josh here. I'm here on a Sunday working on a little project, but thought it'd be a good time to show you a sweet demo of what the Demuths toolmaker's cube is really good at. So in the next couple of stories, I'll walk you through this workflow and what we can achieve with the toolmaker's cube. So just some context, I've posted about this a little. This is a part that's made from 316. So it's non-magnetic, and it needs some precision integrated into it. Off the mill, what happens is that this sort of warps and twists. All the internal stresses have an avenue to twist everything out. So we just do a quick lapping step by hand to get one plane reasonably flat, so it's not just riding on 2 points. Then what we do is we map out the error, the parallelism error, and that's what we see here. So these are numbers in microns. You can see it's actually quite twisted. Our 0 is here. We've got 16 microns out here. It actually gets a bit worse. It's probably close to 20 microns here. So what we're going to do is we're going to grind one side, get it reasonably flat, flip it over, grind the other side parallel, get it reasonably flat, flip it over again, and do this maybe 2 or 3 times until we get less than maybe, I don't know, we shot for around 2 microns total parallelism on both faces. The only problem is that with this sort of construction, even if you bend it, like twist it, something is still stressed, and anyway, but around 2 microns. So it's flip, 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 flip. But because it's not magnetic, it's very challenging to hold. So what we've got here is the Demuths cube setup. Adam's going to love me saying this 1,000 times. We've got a back fence here that's adjustable, and you can see we're riding pretty close to the part height, which is important. And then we've got just a lip here, so it's going to slot in against this way. This is less critical, but we're just nipping it. We're not really wrenching down on it. And then as I said, we're pinning it from this side, and we've got these adjustable clamps that hold with a threaded rod that's just pinning it against this back fence, and you can see it's very close to point contact. So a couple of things I want to point out. The first is the forces. What forces do we have acting? From the mill, this side here and this flat plane, they're pretty square, but nothing's ever perfect. So if we apply too much force, what can happen is this can all tilt and warp. So these forces, they're best when they're aligned as perpendicular as possible to the fence. So if we're pointing down and up, we can influence this in a different direction. Sometimes that's good. Sometimes you'd want to influence it to actually grind it in better. But in this case, we don't want to do that. So you can see how we've got these set up. They're very, very, I don't know, I guess the axis of the force is coplanar to this surface. And so now that we've got the forces sort of analyzed, and just to repeat, if we're pointing this way or that way, we're going to definitely influence how this part is sitting on this surface. So what we've got here is the part, it's not clamped down, but it's basically wrung. It's not really wrung, but it's very, very tight against this surface here because it's been lapped. It's not lapped perfectly, mind you, but it's riding on a plane rather than just a couple of points. And what I've done is I've measured out the deviation on the granite. So without any of the fixture or any clamping forces, we have a map of the parallelism. So now as we tighten these threaded rods to pin it up against this back fence, we can see if we still have that same map. If we've influenced another twist or if we've kicked the part over, we can check that. So here in this demo, this is one side, they're both loose, and we're going to slowly tighten this up and see what happens with the indicator. So this is tight, like this is probably way too tight now, and you can see it just start to bend up, and that's what we want to avoid. We want to avoid influencing the part too much. We're just pinning this against it, and it's going to sit on the surface grinder as we grind away that top surface, so we don't really need too much force holding it down. That's more than enough. And so if we come over to this side, you can see we're about 14, which is good. We're just going to pin this down too. So another comment on the forces. Our contact point is roughly in the center of this part. If the threaded rod is still parallel to this plane but is acting below or above the part, we can still influence the twist. So despite us getting this right, we can still be hitting the wrong spot. So you can see we're quite central. And that's pretty important as well. We've noticed that, or at least I've noticed that if you're not roughly in the center, you're going to kick this part in a way you don't want. So okay, so we're pinned down more than enough. Probably too much. After this is finished recording, I'm gonna stop it. So we got 0 here. We got about 8 there. This is going to go up to 16, 14-ish, and 12. And so you can see we haven't really influenced how this part is sitting. It's really good. And now when we grind this in, the hope is that everything stays good, stays okay. And when we flip it around, we can do the same process, map the error out. And that's how we get this 300 series steel pretty parallel. Hope you enjoyed this. I'll probably keep posting a few more tidbits. And yeah, so we're over here at the grinder. We've got our cube with our spigot installed. This is on an Aroa interface. You could easily have this just as a flat plane and mount directly on the magnet, but we've got this on the Aroa so we can take it to the mill if we needed to. And then we just put it on there, and now we can start to grind all this in. So you can just see we've touched off from that corner that's high, and we're going to go very slowly, 1 micron at a time, just down to our 0. To be completely honest, we might not even clean up there totally because we still have to flip a few times. But yeah, everything's tracking so far. It's always fascinating to see how the warp sort of changes between part to part. There's some consistency, but the material stress is not that homogeneous. You can see that contact patch growing. So we've just cleaned up. I think we took about 25 microns off. And yeah, just a few more spring passes, and then we'll go back to the surface plate to check out how we did. So we're scratching up our nice surface, but it doesn't really matter. And you can see it's not 100% perfect, but it's a lot better than what we had. So yeah, that's the Demuths Toolmaker's Cube. Very, very handy piece of kit. Incredibly well made. Adam is a wizard when it comes to these sorts of things, and tell you what, definitely could not have done many jobs without this thing. So yeah, I hope you enjoyed this little thing, and if you want to see more, let me know. Some jobs obviously we can't share, but jobs like these that are NDA-less, we can. So enjoy. So this is after like, I don't know, 4 flips, I think. It's not perfect. Oops, this is challenging to do one-handed. I think we're about 3 microns in total at the worst spot. That's like -2. Go here. So yeah, the spec is 5 microns, so in the spec, and there's some other operations that still need to be done, which might bow it out a little bit, so I might have to go back and flip it again, but I'm pretty much there. Woo! So this is the next setup. It's the mag chuck on the Kern, and we've got a little sort of plate here that we've ground very parallel, so it's got the part, 2 counterbore holes so we can screw into these threads, which are very convenient. We've just nipped them down. Now we're going to mill this pocket to size. We're going to flip it over and then mill this other pocket to size and sneak up on the distance between these 2 pockets, pocket 1 and pocket 2. So that distance is really, really important. And on the HT, this is actually really good. You could easily do this on the grinder and get a wheel that's, you know, gonna fit in there and just like swipe it in one pass. It's probably what I should be doing, but I'm not that confident on the grinder, especially in that Z-axis. We've got a servo motor on the Z-axis with a ball screw, so getting that wheel centered in that slot and not gouging anything is yeah, a bit of a challenge. So anyway, that's that's this next setup. And what's really important is that the probe height and the tool height are really, really good. So you have to set the tool incredibly well. So currently I've probed this for Z. We've got 14 microns of skew that we're going to correct. And then I've just centered it on this slot. And since I've got the C-axis, I've just probed in this edge. And that'll give me my rotation. So it's, yeah, the next thing is to run, here we go, this toolpath here. Got just some basic facing. Well, it's not really facing, but like pocketing. Just to size. And then we can measure with the probe a bunch of points to see how well we did. Take this block off, put it on the surface plate, and that'll just verify what we've done. Once we get a good plane, then we can use that as a datum, flip the part over, and then mill the other pocket relative to this one, and be pretty sure that we've got everything right. So we've got our program loaded, our tool's in there. We've gone through the whole rigmarole of offsetting the tool and getting the length perfect relative to the probe. What I want to show you is something really cool on the HD. So here we have our PLC compensation for the Z height. I've literally just turned the spindle on. Usually when the machine's not running, it's at 0. But the spindle is just a big heater. That's all it is. And this whole column is actually made from aluminium, the core of it. And as you turn the spindle on, you generate a lot of heat. And even though there's active cooling and all these things, everything expands and the spindle grows, and the machine is intelligent enough that it compensates the Z-axis growth preemptively based on a software model. So there's a model, a compensation graph, basically like a lot of points that get interpolated between, that compensates the Z-axis growth. So what we're going to see is the real-time compensation of the Z-axis. So we're going to go spindle on, and you're going to see, I'm going to turn it on 3, 2, 1. There we go. So it instantly jumps. Currently we're, spinning. Can't really see that. It's about 10K, so very low on the spindle speed, but it's climbing. It'll climb up to, I think maybe 15, 16 microns at around 10,000 RPM. This will peak at 40,000 RPM. I think we've got something like 90 microns, or maybe even 100 microns of growth. So currently the Z-axis is getting pulled up by that amount as the growth is happening. So you can see that instant jump. That's what happens when bearings move around. You get this huge jump of energy dumped into the machine, and the temperature just spreads through the Z-axis. So this really helps us sneak up onto those last microns, but we still wait for this to stabilize a little. We've milled it. Now we're just checking it to see what the probe says. We hit cycle start on probing position for Z minus. Probe comes down, touches off, and we're 0.5 microns, which is pretty good. I'm going to leave it there. I'm not going to touch it too much. And then take it off. We just double check on the surface plate, flip it around, do the other side, and see how close we get. So this is just a check. We're pretty good. Yep, so that means that everything's correlating between the surface plate and the magnet while the part's still on the fixture. So now the true test is going to be us bolting this off and seeing what happens when it's not constrained. Okay, so we've taken off the screws. The part can actually still slide around. It's sucked on a little bit just because of the oil. But what I want to see is what happens when we've released the screws. I can't, undo the screws while it's on the surface plate. So we go here. Pretty good. So that means we're not really influencing it too much with the screws on this little sort of fixture plate, which is good. So now we're just checking that top plane again to see if anything's moved, and we're still pretty okay. I think we might, we're not better. We're about the same. We're still about 2 microns, which is good. That's actually really positive. Nothing's moved. By us milling here, it's not caused anything to like warp or twist. So we can move on now. We can flip this over and do the other pocket over on this side. So this is our measuring setup. We've got this part riding on a gauge block. It's sort of acting like a little riser. Side note, best investment that you can ever get for your workshop is a cheap economy set of gauge blocks. Really helpful for things like this where you don't actually want to use the good ones. Anyway, I can't really do this two-handedly, but we just probe this surface where the ruby is now. That's our 0, and then we move over here, and that gives us the distance between the two planes. Obviously, it's going to rock. It doesn't want to, and it's very feel-based, but you can really feel when it's seated, and I would be comfortable especially with this indicator, I'd be comfortable within a micron on this sort of setup. So that's it. We've got that dimension, 125 plus 5 minus 0. Yeah, we're on the high side, but what you'll notice on note 2, measure dimension and engrave at indicated position over here. So they don't really mind what the dimension is as long as it's measured and indicated. So they use this for some calibration of something. I'm not 100% sure what it's used for, but this has to be one of the most challenging parts we've done. And yeah, I don't know, it's definitely pushed my limits of what's possible, especially on the grinding side. That's new to me. I've only been doing that for like 3 or 4 years, so I'm definitely not stainless. Anyway, thank you very much, guys, for watching this pretty elongated story, and let me know what you think. I don't know, I can't really do this on every job, but if you liked it, let me know, and yeah.